Hi, this is Mr. T with a tutorial on solving systems of linear equations. When we talk about a system of linear equations, we're talking about multiple equations, and we are looking for single solutions or common solutions that will make all of the equations in the system true. To solve a system, we need to have in the system as many equations as you have of variables. In this tutorial, we'll be working with two linear equations that have two variables. If we had three variables, say x, y, and z, we would need then three equations. The procedures demonstrated in this tutorial can be extended to those larger systems, but the algebra work gets to be a bit more complicated and tedious. So we're going to stick with our easier problems here. We're going to talk about several different ways of solving systems of equations, and we're first going to talk about solving them graphically so that we can understand what it is that we are looking for. So I have a system of equation here, two equations, and let's graph those with, since they're both in standard form, let's use our hide and seek method for graphing. So if we take our first equation and hide the y, I've got 2x equals 1, so my x-intercept is 1/2. And if I hide that x, I've got negative 3y equals 1, or my y-intercept is negative 1/3. These points are fairly close together, so I'll do my best to get a line that goes through them. Oops. And now let's, in blue, do the second equation. This one's a little easier. Our x-intercept is at 3, and our y-intercept is at 3 also. And we'll now try to draw a line through there. And I missed the line a little bit, but it'll be close enough for what we're trying to do. Now let's talk about solving. Remember, we need a single x and y pair that make both equations true. Our red line here contains all the solutions to our first equation, and the blue line contains all the solution to this equation, and so they only have one solution in common, and that's the point right here. And that x-y pair is 2, 1. So x is 2, y is 1 is a solution to this equation. To check out our solutions, we can put them into both equations. So I've got 2 times x, which is 2, minus 3 times y, which is 1, equals 1. And we have to check that out. So we have 4 minus 3 equals 1, 1 equals 1, so the solution checks out in the first equation. Now we have 2 plus 1 equals 3, 3 equals 3, so it checks out. Now the solution we find has to make both equations true. Now for this particular system, this pair of x, y is the only pair of x and y that will solve both equations. Let's look at a second example, and this is going to be to point out that trying to solve graphically, unless you're using a graphing calculator, can be problematic. So here we have a new system of equations. So let's graph the first one in red here. So if I hide my y, I've got a x-intercept of 4. And if I hide the x, I have an x-intercept of negative 2. So let's draw a line through that. Let's see if we get the slope here. We're going to be coming over from, say, here. Let's go through those points. And let's graph the second line. We'll do that in blue. So our x-intercept is 5/2, 2.5. So we're right here, approximately. And our y-intercept is 5. And let's draw a blue line through those points. See if I can get it lined up this time. Pretty good. But we can see that the x and y coordinates at our intersection, which would be the solution to this system, are not exactly on the grid. Now that could either be because I didn't graph the lines accurately, or in this case the solution is not integer values. So we could guess at or approximate the solution, but we're not going to be able to get the exact solution. So given the problems with the graphic method, we're going to talk about how we can solve these algebraically. So let's go to our next slide. The first method that we're going to use is called the substitution method. Now here's our system. Now remember, the solution is a single pair of numbers for x and y that make both equations true. So the y value at the solution point, the y value in each equation, those two y values will be the same. So since those two y values are the same, the algebra principle here says that these two equations also have to be equal. So when these two equations were both solved for y, we can set these two equations equal to one another. So we have 2x plus 5 equals negative 2x minus 3. And now we have a single equation with one variable, which we learned how to solve in Chapter 1. So let's get the x's on one side, and let's get the numbers on the other. So we have 4x equals negative 8. We'll divide by 4, and we get x equals negative 2. Now that's the x value at the solution point for these two equations. We need to calculate the y, so we need to take either of our original equations and substitute in the x value that we just found, so that we can find our y value. So here I get negative 4 plus 5, or y equals 1. So our solution to this system is at negative 2 and 1. And again, if we wanted to verify that that works, we could put these into both equations and verify that they make both sides true. So again, we did a substitution. We set this equation for the y over here. So we set those two equations equal. Now, many times we won't have both equations solved for y, and in this particular case, neither equation is solved for y. But we can still use the substitution method if we can solve one of the equations for a single letter. So let's take this first equation and solve it for x. So I can subtract the 2y to the other side. And then I have to divide everything by minus 1 to change the sign of the x, and we get x equals 2y minus 3. Now the value of x here, this x at the solution point, is the same as this x. So we can do a substitution. We can take this proxy, or this value for x, and put it into the other equation for that value of x. Now you always have to substitute into the equation that you didn't solve. So if we come over here and do that, I'm going to replace that x with 2y minus 3. The rest of the equation stays the same as equation number 2. And now we have again an equation with only one letter, so we know how to solve that. We're going to distribute the 4. And now we can combine those two like terms, so we have 3y minus 12 equals negative 3. We can get the y by itself. So we have 3y equals 9, and we divide by 3, and we get y equals 3. Now this is the y value at our solution. We need to find the x value. Now we could plug that back into one of these original equations, but we can also plug it into this equation. So x is going to be 2 times y, which is 3, minus 3, which is 6 minus 3, or 3. So our solution that makes both of these equations true would be 3, 3, x and y that make these true. So this method in these two examples is called the substitution method, and again, if you can solve one or both equations for a letter, and it doesn't have to be y, we showed here that you can solve for x, this method works well. Now let's look at a different example where the substitution method doesn't work as easily. So we have a new system here, and solving either of these equations for x or y, we're going to have lots of fractions. And many of you have difficulties when we're trying to work with equations with the fractions. So we're going to use a method called linear combinations. And the whole theme or reason linear combinations works is an algebra principle that if these two things are equal, we can create a third equation by adding these two equations together. So we add like terms. So we're going to essentially, since the way they're lined up, add in columns. So if I add here 3x minus 3x is 0x, or just disappears. Here I have 7y, and negative 16 plus 9 is negative 7. I was able to eliminate one of the letters by adding these two equations together and get a new equation that has only one letter. Sometimes this method, because of what we just did, is also called the elimination method. So now we solve for y and we get negative 1. Now we have to find x, so we have to put it back into one of these two equations to find x. So let's substitute into the first equation. And now we have negative 5 here, so we'll add it to the other side. So if we add negative 5 over here, we get negative 11. And if we divide by 3, we get x equals negative 11 thirds. So we can see here that the answer was a fraction. So if we had tried doing this with the substitution method again, we would have had a number of fractions to deal with. So our solution is at negative 11 thirds, comma, negative 1. And again, we could verify that by putting this back into each equation and show that it solves it. So again, the key focus is to get opposites, either 3 and negative 3 here, or we could have tried to get opposites here. We want one of the letters to disappear. In this case, it was too easy because the original equations had opposites. So let's look at what happens if we do not start out with opposites. So in this case, we need to create opposites. Now, one of the things we are allowed to do is multiply both sides of the equation by a number, and we maintain our equality. So we want to create opposites either in the x's or the y's. So the common multiple here for x's would be 35, so we would need to create a positive and negative 35, or 12 and 8 both divide into 24, so we could create positive and negative 24. They have the same sign, so I'm going to multiply. I'm going to create 24s here, so I'm going to multiply the top equation by negative 2. So I'm going to multiply all the way across by negative 2 and generate a new equation. So now I have negative 14x plus 24y, and negative 2 times negative 22 is positive 44. Now I'm trying to create 24s in front of the y, so I have to multiply this equation by 3, and I'm going to multiply by positive 3 because I want this to turn out to be negative 24, so it'll cancel out. So now I have 15x minus 24y, and 3 times negative 14 is negative 42. Soon as you create your opposites, we do the linear combination. So we're adding the two equations. So here I get x, those cancel out, and I get 2 when I add those. So now I have my x value. Now I need to find y. I can plug into either of those equations, or it's probably easier, plug back into the one of the original two equations. So let's plug into this first equation here. So 7 times x, which we just found to be 2, minus 12y equals negative 22. That's 14, so I'm going to subtract 14. So negative 12y equals negative 36, and we divide by negative 12, and we get y equals 3. So our solution to this system, the values that make both equations true, are the 0.23. Again, this is called the linear combination method because we are combining two equations, and in the process getting rid of one of the letters. When we have problems, most of the time it's not going to tell you which method to use, so another skill is to choose the appropriate method. So if you look at the original equations, if one or both of the equations are solved for a letter, either x or y, or it's easy to solve one of them for a single letter, your substitution method, I spelled this wrong here, there's supposed to be a missing T here, sorry. And if both equations are in standard form and you look at the coefficients and you can easily create opposites like we just did, you want to use linear combinations. If it's not obvious between the two, then I recommend you just work with the method that you're most comfortable with, the one that you seem to have the most success with, and use that, because both methods will always work. Now to wrap this up, so far every problem we've had with two linear equations, we've had a single solution. There are two special cases that we need to look at here to wrap up. So let's look at this with the first special case, and let's look at it with first graphically. So if we graph the first equation, our y-intercept is at negative 5, and our slope is 1. So we have a line coming up through here. And if we look at the second one, we have a y-intercept at 3, again a slope of 1. And let's draw the line, and we have here our second line. And these are parallel lines. Where do those lines intersect? Because we saw at the very beginning the solution to this system are where the lines intersect. So from the graph we can tell that there is no solution that we can find that will solve both equations. Now we don't want to resort to graphics, so let's look at this. Now this problem has both equations solved for y. So algebraically we could use our substitution method and set each equation equal to each other. And now solve. So we would be trying to get the x's on one side, and notice what happens here. The x's cancel out on both sides. And we're left with an equation that can never be true. It's impossible. There's nothing we can plug in here that can make negative 5 equal to 3. So this is never true. And that's the signature when we are doing things algebraically. That means no solution. So two things will happen when we solve. You will have the x's disappear, and you will have an equation that can never be true. This can come out both using substitution method or the linear combination method. Let's look at our last case here. Let's graph these two lines. To look at it graphically first, so we have a y-intercept at 2 and a slope of 1 for the first equation. Let's see here, try to get my line right. And let's do the second one here in blue. We have a x-intercept at 5 divided by negative 10 at negative 2. And we have a y-intercept at negative 10 divided by negative 5, positive 2. And look what just happened. We have the same line. So the two lines are on top of each other. So where do they intersect? Well, they intersect at every point along the line. Now, it's not any xy pair. If we picked an xy over here, doesn't solve either equation, but all the solutions for each equation solve both. So in this case, what we can say is that we have infinite, I can't spell here, sorry for the writing, infinitely many solutions. Or we can just say infinite solutions. Now again, let's look at this algebraically. Now in this case we have one equation solved for y, so I'm going to use substitution again, but the same thing could work using linear combinations. So I'm going to keep the x, and we're going to put in for the y x plus 2. And we're going to distribute. Combine like terms here, those cancel out, and we end up with negative 10 equals negative 10. So again, all my x's disappeared, but in this case we end up with something that is always true. No matter what value of x we put back up here, this equation would always be true. That's our signature for when we have the special case of infinite solutions. So to wrap up, when we have a system of equations, normally we end up with a single xy pair that solves, but there is the potential in some situations where we have no solution, and in other situations where we have an infinite number of solutions. Good luck working your problems.